Today, we're going to go through some practice problems for Chapter 5. First, we'll go through the rules for assigning absolute configuration. Remember, this is the Kohn-Ingold Prelog system that we also learned to use for double bonds. So using atomic numbers, we're going to prioritize the 4 groups that are attached to the chiral center. Number 2, we're going to arrange the molecule in space so the lowest priority group faces away from us. And then we'll count the priorities, excuse me, 1, 2, 3 in order of progress in a clockwise or a counterclockwise direction. If the priority groups are clockwise, that will be R, and if they are counterclockwise, that will be S. We had a couple tricks that we talked about. The first is that the lowest priority group, if the lowest priority group is pointing out at you, then we would assign R or S and take the opposite answer. Because remember that according to our rules, the lowest priority group should be pointing back away from us or on that dashed line. So if the lowest priority group is pointing out at us, for instance, on the wedged line, then we're going to assign RRS like normal, but take the opposite answer from what we get. The second trick here says that if we take 2 of the groups and we switch them, so we make one swap, switch 2 of the groups, this is going to give us the enantiomer. So for instance, if I have a wedge and I turn it to dash, that means I've switched the wedge and the dash, the groups that are on the wedge and the dash. And this will give us the enantiomer. If I do 2 swaps, so 2 switches of 2 groups, I'll get back to the original configuration. And then trick 3 says that a double bond counts as 2 bonds to that atom. So a double bond to an oxygen would be like there are 2 bonds to oxygens. So let's go through and assign RS to some of these problems. In this first problem, we have one chiral center, and we notice that the hydrogen, well, let's assign priorities to the group. First of all, there is a hydrogen that is pointing back. That makes the 4th group, right? To be a chiral center, there must be 4 different things attached. So the hydrogen is pointing back, and we're going to assign that the lowest priority. Remember, we're using atomic numbers to assign these priorities. And coming out from the chiral center, the lowest atomic number is the hydrogen. The highest atomic number is the oxygen at 16. That's going to get priority 1. And then we go to these 2 groups, and the one on the left is a carbon and the one on the right is the carbon. And remember, we'll look now, since it's a tie at carbons, we look at what's attached to those carbons. On the right, there are 3 hydrogens. This is a CH3 group. 3 hydrogens attached to that carbon. On the left, there are these 2 hydrogens, but then this carbon is also attached to a carbon. So on the left here, this carbon is attached to CHH, and therefore the left gets a higher priority. So we've got 2 and we've got 3. And then we proceed to determine if these priorities go in a clockwise fashion or a counterclockwise fashion. And you can see here it's 1, 2, 3. That is counterclockwise, and that gives us S. On number 2 here, we have one chiral center. Remember, this is not a chiral center over here because there's 2 of the same groups attached. So 2 methyl groups. Remember, to be a chiral center, we need 4 different groups attached. So from this chiral center, the priorities, we've got a hydrogen that's wedged. So we're going to give that priority 4. And then the highest atomic weight is the fluorine at 19. We're going to give that priority 1. And then we've got 2 carbons to compare. Okay. And we've got a carbon here on the left that's attached to, there's a hydrogen, because remember, carbon needs to make 4 bonds. So there's a hydrogen and 2 carbons. So on the left here, we've got carbon, carbon, hydrogen attached. Over on the right here, we have 2 hydrogens and a carbon attached. So carbon, hydrogen, hydrogen. So the first one is a tie at carbon, but the second one, the atomic weight of the carbon wins out. So the left gets priority 2 and the right gets priority 3. Okay. So now we want to assign RS to this. We're going to, that is counterclockwise. So that is S. But remember that our lowest priority group is on the wedge. It's pointing out at you. And trick 1 says if the lowest priority group is pointing out at you, it is not pointing back, then we're going to take the opposite of what we see. So that answer is R. On this next one here, this is a Fisher projection, and we have our chiral center here in the middle. And our the thing we need to remember about the Fisher projections is whatever is on the horizontal is wedged, and whatever is on the vertical is pointing back as a dash. So then we can just assign RRS like we've been doing. So our chiral center is here in the middle. The H is the lowest priority group that comes out from our chiral center, and the O is the highest priority group. Okay. We then go down and up, and we can see that both of these have carbons. So we're going to need to compare them. That's a tie, a carbon, both of them having carbons. So we need to compare these. The bottom carbon has 2 hydrogens and an oxygen attached to it. So H, H, and O. The top carbon, remember this is trick 3, it said if the atom is attached to a double bond, we count it as 2 bonds to that atom. So this is just for our rule purpose. So we pretend like this carbon is attached to 2 oxygens here. And then it's actually attached to a 3rd oxygen. So we can clearly see the first oxygen is a tie, but then the second oxygen wins out. So the higher atomic weight is up here on the top. That gets a 2, and the bottom gets a 3. That gives me a counterclockwise, which is S configuration. However, remember this lowest priority group is on the wedge because it's in that horizontal position, and therefore the configuration of the center is actually R. The next one just shows us how we would have to determine the configuration on a larger molecule. And so we've got 2 stereocenters here, 1 and 2. We're going to start with this first one, and we can see that there is a hydrogen pointing back, and that's nice since our lowest priority group is going to be pointing back. So our chiral center is here that we're looking at. The lowest priority group is pointing back. I'm going to give that a 4. And then we've got a carbon, and an oxygen. The oxygen gets priority 1. Now we need to compare the carbon on the left and the carbon on the right. Okay, the carbon on the left is attached to a carbon double bond. So that, remember we said Trick 3, we pretend like that's 2 carbons, and then it's also attached to another carbon. So carbon, carbon, carbon. There's no hydrogens attached to that. The carbon on the right has a nitrogen attached to it. Then there's a hydrogen back here. Okay. And it has another carbon. Okay. So remember, when we're comparing these 3 groups, we're going to look for the first thing that we do is we compare the highest atomic number atoms. So on the left, the highest atomic number is a C, and on the right, the highest atomic number is a nitrogen. So 14 wins out over 12, and that means this group over here on the right is going to get the 2. And that means the group over here on the left is going to get the 3. So now we assign RS. We go 1, 2, 3, and it means that this stereocenter is going to be R. Okay, we're going to clear some of our space here. And now we're going to assign the second stereocenter. So we're looking at the stereocenter here. We've got a nitrogen attached. Remember, there is also a hydrogen back here. If the nitrogen is wedged, that means the hydrogen is going to be dashed. The hydrogen is pointing back away from us. That's where we want our lowest priority group. So we're good to go. We're following the rules nicely here. So lowest priority group is 4. Then coming out from this chiral center, we have a nitrogen, a carbon, and a carbon. Okay, so nitrogen is going to get priority 1 since it's the highest atomic weight. And now we need to compare these 2 carbons here. Let me get rid of a little bit more of this drawing over on the left. Okay. And so we're going to compare the carbon on the right and the carbon on the left. The carbon on the right has 2 hydrogens attached to it and an oxygen. So we've got O, H, H. The carbon on the left here has an oxygen, a hydrogen, and a carbon attached to it. So oxygen, carbon, and hydrogen attached to it. So we're comparing these 2 sides essentially. The top is a tie. So we look at the highest molecular weight first. The oxygens are a tie. Then we go to the next highest molecular weight. On the left, we have a carbon. On the right, we have a hydrogen. So the left is going to win out. So that is going to be, the left is going to be priority 2, and the right is going to be priority 3. So now we assign RS. The H is pointing back, that lowest priority group. So what we see is what we're going to get. And we get R. So both of these centers are R on chloraminophenol. My eraser's not working here. Okay. All right. So the next thing that we want to do is, now that we've learned how to assign RS, is we're going to look at the relationship between these different compounds. So our choices are they enantiomers? Remember, enantiomers have the same physical properties, and they only differ by their optical activity. So they rotate the plane polarized light the same magnitude, but in opposite directions. And that's the only way we can tell the difference between enantiomers. So diastereomers have different physical properties. All right, but when we're looking at these, what we're going to do is An enantiomer is going to have the opposite configuration at every chiral center. So maybe we'll just put opposite configuration at all chiral centers. So I look and I go, okay, this chlorine is dashed, now it's wedged. This chlorine is wedged, now it's dashed. So these are the opposite configurations at every chiral center. That means these are enantiomers. If I went and assigned R or S to these, let's say I'm not going to do that right now for sake of time, but if both of these on the left were R, then both of these on the right would be S. Okay, these are enantiomers. This second compound, we've got wedge, wedge, and now we've got wedge dash. So we've got one that's the same, one that's different, and these are then diastereomers. Remember, diastereomers must have one configuration that's different, but not all of the configurations. I've got two problems that are somehow superimposed on each other. Do not know what happened there. Okay, well, I do want to do these problems. So this is supposed to be two different problems, but for some reason they're on top of each other. So we're looking at these two molecules up here on the top. Okay, these two molecules are actually the same molecules. I want you to imagine taking this second molecule and just, let's get rid of the eraser. Why can I not erase? There we go. Hold on. Okay. Maybe I can put a little space between these. Let's do that. All right, well, I'm just going to move on, I guess. There we go. There we go. Okay. So let's do this first problem. I want you to imagine taking this second molecule here and just flop it over. And you can see, like if I made a model of this, this OH is pointing out towards you. And if I flop it over, it's going to turn exactly into this molecule. Okay, so visually, if I can do a 3D mental gymnastics, I can see that these two are the same compound. Okay, I can also use some of our tricks to see if they're the same compound. Do you remember we said if we do two swaps? So if I can't do mental gymnastics, I can try to use our trick. If we do two swaps of groups, then we're going to be at the same molecule. So think about this. If I take the OH and the H and I swap them, okay, so let's do that. Now the OH would be dashed and the H would be wedged. So that's one swap. If I do a second swap, which means changing these groups, now I'm going to end up at the same molecule. Okay, so two swaps and I get back to the same molecule. So you can either try to do mental gymnastics where you flip the molecule and you can see that they would line up perfectly, or you can use our two swaps in order to see that these two are the same molecule. This is a molecule that has a plane of symmetry in the middle of it, and it therefore is not chiral, and these two are the same molecule. But again, you could take this molecule here on the right, and if you just flip it over, the OHs are going to line up, and also both of these groups are going to line up. So these are also the same molecules. They're identical, is what we would say. Okay, the next one on the Fisher projections, it's pretty easy to check if these are enantiomers or diastereomers. First, I just want to make sure that the groups at the top and the bottom are the same. So I've got the aldehyde, I've got the CH2OH, that's good to go. Now all I'm going to do is look at the chiral centers. On the first chiral center, there's an OH on the left. On the right, there's an OH on the left. So these ones are the same. On the second chiral center, there's an OH on the right and an OH on the left. So those ones are different. Okay, and remember, if we have one chiral center that's the same and one that's different, that means that these must be diastereomers. Our definition of diastereomers was that there is at least one chiral center that's different, but not all of the chiral centers. Okay, on this next one, I can look, I need to look at whether these two substituents are cis or trans to one another. So if I am practiced at this, I could say, okay, this is this methyl group here on the left is up, and this one is up in relationship to the hydrogens. So up, if I wanted to draw a bond line structure, that means those methyl groups are cis. Okay. And then I need to look at the second structure. This methyl group on the right here is up in relationship to the hydrogen, and the methyl group on the left here is down in relationship to the hydrogen. So that bond line structure looks like this. So we've got same, then different. So again, these are diastereomers of each other. Okay. If both were flipped, then they would be enantiomers. But since we have one that's the same and one that's different, these are diastereomers. The next problem says, how many chiral centers are there? So I just need to recognize the chiral centers. And remember, a chiral center has 4 different groups attached to it. So we see this first one here, okay, because remember there's 3 bonds to that carbon, but there's also a hydrogen. So we've got one chiral center here. We've got a second chiral center here. These are different groups attached to this carbon. They're the same here, CH2, CH2, but then when we get to the next carbon, they're different. So that means that each side is different. So this is a chiral center. This is also a chiral center. Again, when we go out from that chiral center, we have a CH2 group and a CH2 group. That's the same. Then we have a CH2 group and a CH2 group. That's the same. But when we get farther around the ring, now we have different groups attached. So that means one side is different than the other side. So this is also a chiral center. And then we have a 4th chiral center here. How many stereoisomers are possible? We use the formula 2 to the n, and there are 4, so that's 2 to the 4, and that equals 2 times 2 times 2 times 2, or you can put that into your calculator. That gives us 16 stereoisomers. So we should be able to draw 16 different variations of that molecule. Okay, the next compounds, it says which of the following are meso. So I'm looking for a plane of symmetry. When I'm looking at these Fisher projections, the first thing I want to look at is just to make sure that in order for the compound to be meso, I need to have the same groups on each end. So I have those CH3 groups. And then I want to look to see if basically if I folded this thing in half, is it going to look the same on both ends? And I do have a plane of symmetry right through the middle there. One half looks like the other half. So this is a meso compound. Remember, meso compounds are achiral. That means they have no optical activity. If I put them into a polarimeter, it would read 0. Okay, on this compound here, you can see right away that one half is different than the other half. And so that is not going to be a meso compound. On these chairs, I need to determine if they are cis or trans. If the two substituents are cis, then it may be a meso compound. So in this case, I've got the methyl group up and I've got the methyl group up. If I draw a bond line structure for this, that gives me both methyl groups up, and you can see there is a plane of symmetry through the middle. This next compound is, so this is a meso compound as well. So we have two meso compounds so far. On this next one, it's a little different. You need to use some mental gymnastics again. And in this case, you might think to yourself, these are trans to one another. This is not a meso compound, but it is. Because we draw in this zigzag fashion, we need to rotate the bond around. So if I rotate around this bond, that means the OH is going to flip up. This is why models are recommended for this class. It's just super easy to see if you have a model and you can rotate this around, like when we had our Newman projections. And so when I rotate this around, now you can see that there's a plane of symmetry down the middle. Okay, so one half of the molecule looks like the other half of the molecule. So this is a meso compound. And then you can imagine if both of these were wedged, this is not going to be a meso compound, because if we rotate just like we did over here, we're going to rotate this compound number one around, and the first one's going to stay the same, and now the second one is going to be, second OH is going to be back. So there is not a plane of symmetry in that one. And then the third one here, you have both of these groups cis, and we do have this plane of symmetry straight down the middle. So this is also meso. All right, so those are just kind of the practice questions, the chemical skills type questions. But remember, there were other things where we talked about optical activity. We talked about EE. We talked about how to calculate EE, which was the major enantiomer minus the minor enantiomer, and that would give us a percent EE. The percent EE is the amount of excess of the major enantiomer that we have. And then also we said if we have a mixture of 50-50 R and S, that is what we call a racemic mixture. And it has no optical activity. So if I put that into the polarimeter, it's going to read 0. What else? I guess I'm going to leave it at that. All right, thanks for watching and good luck on your test.